I'm going to go back to the textbook to just talk about accuracy and precision. So instead of writing this out because it's a very visual thing, accuracy is described of how close you are to the real value or the accepted value of something, and precision is how close you are to how close your values are to each other. So if you look at this cartoon, basically, high accuracy, low precision means that you are around the bullseye, you are around the values that you expect to get, but your values aren't really that close to each other, so it's low precision. And then the second bullseye is not anywhere close to the center. It's not anywhere close to where you're supposed to get, but all of the values are very close to each other, so it's low accuracy but high precision. So that's just the difference between these. That's going to be something that you're going to need to know the difference between. And it's something that you can just learn to do. And then basically, if you have a low accuracy, high precision thing, if you have an experiment that has low accuracy but high precision, for something that you know isn't going to be change, that's been scientifically verified, that you verified before, then that probably means that your instrumentation is wrong or your methodology is wrong. And then for uncertainty, uncertainty is the inevitable differences, the inevitable changes that you're going to get, the inevitable deviations from the mean that you have to get when you're taking measurements or you're doing estimations. So how it's written out. Okay, come on. Is that you have some value and you have a value A, and that is written out as A plus or minus delta A, where delta A, this is a small delta, is the uncertainty of the values. So what this might come down to is, it might come down to instrumentation. It might be like you have a stopwatch, it has some uncertainty because it only counts once per second. So you would have an uncertainty of 1 second in that case, or you have a caliper that only goes up to 0.0025 inches. That's how precise the instrumentation is. So that can be the uncertainty, or you can have just experimental uncertainty, because when you talk about this, when you do all of this, it turns out that quantum mechanically, what you're doing can never have perfect certainty. You can never know everything exactly as it is because of something called Heisenberg's uncertainty principle. So there's always going to be this uncertainty no matter how good your instrumentation is. And then we use the small delta because we normally use big delta to signify big changes. And then we use small delta to represent uncertainty because it's talking about small changes. And then the percent error is going to be defined as delta A over A times 100%. So if you have like an uncertainty of 0.5 meters off of a measurement of 1 meter, that's going to be an insane uncertainty, but it's going to have an uncertainty of 50%, or it's going to have a percent error of 50%. And then another thing, the other thing to note about uncertainty is that if your value falls within this uncertainty, then that means that your value agrees with the scientific value. So you have G, which is the acceleration due to gravity on Earth, which is G equals 9.8 meters per second squared. So if you make a measurement and you find that it's 10 meters per second squared plus or minus 0.5 meters per second squared, then that would agree with each other because 9.8 meters per second squared is within 0.5 of 10 meters per second squared, right?
Right.
And then I think two more things that I want to go over. This is ending up taking longer than I expected, so I apologize for that, but so we talked about significant figures earlier. So we have the rules. So we have to decide on the rules of significant figures. So what we need to do is for zeros, in a significant figure, we have 2.02 times 10 to the 30th, or 2.0 times 10 to the 30th, or 0.02 times 10 to the 30th. So the number of significant figures for each of these is different. So for significant figures, the zeros can count or they cannot count. So in this case, because the zero contains information, it tells you that there's a zeros placed between the 2 and the 2. It does count for the number of significant figures, though. So there are 3 significant figures here. For this one, there are 2 significant figures, or there are 1 significant figure. It depends on how you count it. But since I included the 0 here, then and it came after the 2, then we can assume that we can assume that this significant figure is important. So, or this is a significant figure. So we can assume that it can be like 2.02 or 2.03. We don't know about that. But we can assume that it isn't going to be equal to 2.1 or 2.2 because I put the 0 there. And therefore, it is probably going to be equal to 2 sig figs because that's how you write it out. And then in this one, the 0 is just a placeholder. It doesn't tell you anything except for how far out your decimal place is from the value. So this has one significant figure. So let me just steal the rules from the textbook. Okay, geez, Louise. Zoom is really slow to like switch into nowadays. Or today it's been really slow when I'm trying to switch from the textbook to Zoom. So these are the specific rules for significant figures. So the zeros in 0.053 are not significant because they are placeholders that locate the decimal point. So that's what I said about 0.02. And then that means that there are two significant figures, the 5 and the 3. The zeros in 10.053 are not placeholders, they are significant. So that has 5 significant figures, like the 2.02 that I was talking about has 3. And the zeros or 1300 may or may not be significant, which is basically what I was saying for 2.0, which is why we tend to write in scientific notation. Because if we write in scientific notation, then anything that comes after the first digit is going to be a significant figure because we are indicating that there are these amounts of significant figures, that these are 2.0 rather than 2, and then some number of uncertainty. Okay. So that is important. It's important when you're doing measurements or when you're doing calculations. It's important for that. And then also, in addition to this, we have rules for adding them up. Or multiplying by them. So when you talk about significant figures and you talk about calculations that you do with them, then you can't be more precise than the lower bound of your significant figures. Like you can't be more, if you have something with 15 significant figures, some measurement with a ton of significant figures, because it's very precise, and then you add it to something that isn't very precise, then you're not going to be able to be more precise than the less precise measurement, even though one of your measurements is very precise, the other one brings it down to its level. So what this means for multiplication is that you just use the number of significant figures of the less precise value. So if you're talking about if you're talking about 0.5 over 2.5, this is going to have one significant figure. This is going to have two significant figures. So this is going to be equal to 1 over 5, I believe, which is equal to 0.2, but it's not 0.20 because you have to go with the number of the less significant figures, right? And then when you're doing addition or subtraction, then you have to go to the decimal point of the less significant figures. So if you have 7.507 plus 0.2, then you can only go to 7.7. You can't go to 7.705 or 707 because, or 0.20, because you don't have that much information. You have to go to the value of the less significant figure.